Now that we explored the ancient world, it's time to shift your attention on a more international level. So grab your virtual backpack, sharpen your echo's world, and let's embark on the adventure of a lifetime.
Okay then, let's not waste time talking. Every minute is precious, just like our planet.
You couldn't be more right, but first it is necessary defining the expression climate change. Do you all know what's that about?
Yes, it indicates long-term changes in temperatures and weather patterns. These changes may be due to natural causes like variations in the solar cycle. In the last 200 years, however, the main cause of climate change has been human activities, primarily due to burning fossil fuels like coal, gas, and oil.
Moreover, burning fossil fuels produces emissions of greenhouse gases in the atmosphere, which trap the sun's heat and raise temperatures. Some examples of these gases that are causing climate change are carbon dioxide and methane, which come from using petrol or diesel for vehicles or coal for heating.
Landfills for waste disposal are a major source of methane emissions. Energy, industry, transport, heating, buildings, and agriculture are among the main emitters of greenhouse gases. Emissions continue to rise, and consequently, the temperature of the Earth is rising more and more over the years. The Earth is now about 1.1 degree warmer than 100 years ago, and the last decade there was the hottest record. Picture the atmosphere as our home, as the stage for a celestial performance where the actors are molecules swirling in a cosmic ballet. Within this atmospheric theater, climate change takes center stage from all points of view. Today, though, we will analyze it from a physical and mathematical perspective.
Because we have spent all of our lives living in the atmosphere of the Earth, we have 20 kilometers or so of air pressing on us. We don't feel the pressure because it doesn't just push down, it pushes us inwards from all sides. Our lungs don't collapse because the same air pressure flows into our lungs and presses outwards. It would be a very different story if our lungs didn't contain any air and there was a vacuum inside them.
Yes, and we can prove this with an experiment, for example, by seeing how a plastic bottle collapses if the air is removed from it. The plastic bottle is filled with steam from a kettle so that the air it is replaced with the steam, and the lid is screwed onto the bottle, and the bottle is cooled by immersing it in cold water. When the steam turns back into the water, the bottle collapses due to the pressure of the air outside.
At this point, the question is, how can we measure the atmospheric pressure?
Oh, know that. Did you know that it's possible thanks to the work of physics and scientists who invented the mercury barometer? It's an instrument that is made of a glass tube, sealed at the top. It contains mercury, and at the base of the tubes dips into a beaker, and below the surface of the mercury in the beaker. Atmospheric pressure pushes down on the mercury in the beaker, which in turn pushes mercury up the tube. Mercury barometers measure atmospheric pressure by balancing the weight of mercury in a sealed tube against atmospheric pressure. However, due to mercury toxicity, they are no longer produced.
Guys, but are you even aware that linking the barometer to the sound waves offer a unique perspective of showing how the atmospheric pressure variation impacts the propagation of sound?
You got it! By exploring the interplay between barometric pressure changes and sound transmission, we discover intriguing connection between atmospheric conditions and acoustic pollution. Noise pollution refers to the excessive presence of unwanted sounds in the environment, stemming from different sources such as traffic, industrial activities, loud music, and noisy appliances. Sound waves, which enable us to perceive sounds, can be portrayed graphically using a sine wave. This wave illustrates the fluctuations in air pressures over time.
In addition, as sound propagates through the air, it causes particles to oscillate back and forth, generating waves. These waves exhibit peaks and troughs that indicate changes in air pressure. The height of the wave and the spacing between peaks determine the volume of the sound.
Noise pollution occurs when multiple sounds overlap, making it difficult to hear or concentrate. Visualizing sound waves through sine waves helps us understand how sounds travel and interact in the air, providing insight into why excessive noise can pose a problem.